The first gas turbine problem we are going to solve is a simple Brayton cycle problem. So let's go to chapter 8 in the problems module, and let's go ahead and solve problem 811. We'll copy this problem to the PowerPoint and continue from there. So I've copied the problem here. So let's look at the problem. What is given here is that air is entering the, this is an air standard Brayton cycle. Air is entering at kind of atmospheric condition, 100 kPa, 25 degrees Celsius. And the volumetric flow rate is given. In other words, the mass flow rate is not given, and we know how to convert volumetric flow rate into mass flow rate. The compressor pressure ratio is 12. So if this is 100 kPa here, it will be 1200 kPa at state 2. So it will be 100 kPa here, 1200 kPa, 1200 kPa, back to 100 kPa. And the turbine inlet temperature is 1100 degrees Celsius, right? Okay, so these are some of the data given to us. Even without looking at what do they want us to find, our goal should be to clearly to find state 1, 2, 3, and 4, and then analyze each of the devices, and then try to answer the question. If we know network, heat in, we can find thermal efficiency. Net power output would be W dot T minus W dot C, and the back work ratio is essentially is considered what is the turbine power divided by the compressor power. So I hope you can study the book to some of the definitions that I haven't covered in the lecture. You can go back to the book and read up about that. Okay, so let's get started. The first step, as usual, will be to draw a TS diagram of the ideal Brayton cycle, which we have done a number of times already. Okay, so let's start with the compressor analysis. For that, we need to know state 1, 2, 3, 4. State 1 and 2. So let's write down what you know about state 1. Pressure is given as 100 kPa. And temperature is 25 degrees Celsius. So let's convert temperature to Kelvin. Is 273 plus 25 would be 298 Kelvin. The volume flow rate is given. The volumetric flow rate means what is entering at state 1. So V dot 1 is given to us to be 8 meter cube per second. So what is the mass flow rate? M dot density times volume flow rate. And what is density? Inverse over specific volume, right? Using the ideal gas equation of state, PV equals RT, we get V equals RT over P. So the mass flow rate becomes the value for R for air, this should be the value for R, value for CP, and value for K should be familiar to everybody. K is 1.4, CP is about 1.005, and R is 287. Where do you find these values? Of course, you go to the tables module property tables, and the PG model, common gases, and air should be the first one. You'll find the value of R, Cp, Cv, K right here. Okay, so now that m dot can be evaluated, if you substitute the values, V1 is given as 8, pressure is 100 kPa, R is 0.287, and temperature is 298. If you do the calculation, that comes to 9.35 kg per meter cube. Okay, now that we have found the mass flow rate, let's go and verify using test calc. That will be our constant habit. So let's open up another copy of test and go to the test calc module. And to solve a gas turbine problem, we follow system analysis. It's an open system, specific branch, and as you come down here, you can see vapor power and gas power cycles. If you click here, that brings up different material models, working fluid model we can use. And for a gas turbine, we use a pure gas model, which is PG model that we are using in our manual solution. So this will be the correct one to launch. And we go to the test calc tab to launch the test calc. First step, we select air. State 1 is already our selected here, so therefore state 1 is the inlet state is at 100 kPa and temperature is 25 degrees Celsius. The volume flow rate is given to us as 8 meter cube per second. So that's enough information. We can just click calculate or hit enter to find the state. And the mass flow rate is, oh, we made a mistake, cannot be so high. Temperature is not 25 Rankine, temperature is 25 degrees C. Now, if you notice, the mass flow rate is about 9.35, and I believe what we found was pretty close. 9.35 kg per second, so that's verified. Now let's go to state 2. What is known about state 2? Notice that entropy remains constant, so we can write pressure is, I think the pressure ratio was 12, so it's 12 times 100, 1200 kPa, and entropy at 2 equals entropy at 1. So how can we find temperature? Because we need the temperature to find the compressor work. If the process is isentropic, we can go back to our formula sheet, which is where I believe on this tab, and you notice that if entropy remains constant, we have constant entropy formula for the PG model, and this is equation 11 is a very important equation. You notice that we know the pressure ratio, so P2 over P1 is known, so this part T2 over T1 and P2 over P1 are connected by this equation, equation 11. So we go back using Once again, T2 over T1 is P2 over P1 to the K minus 1 over K. So substituting, we get T2 equals T1 is what? 298 Kelvin. And P2 over P1 is 12. 1.4 minus 1, 1.4. And if you do the calculations, it comes about 606 Kelvin. Let's go and verify this just to make sure. So for verification, we go to the test calc module. State 2, pressure equals 12 times P1. And entropy remain, sorry, not energy, entropy S2 equals S1. And of course, mass flow rate cannot change. It's the same mass flowing through inlet to the exit. As I hit enter, I get the temperature here in Celsius. Let me, in Kelvin, what is the temperature? 606 Kelvin. And I believe we got 600, yeah, pretty close to this answer, 606 Kelvin. But let's make sure, let's quickly draw a TS diagram to make sure we didn't make any mistake. And notice that state 1 and 2 are constant entropy line. And if we draw a constant pressure line, actually you can see this will be pressure equals 100 kPa line, and this is pressure equals 1200 kPa line. And entropy remain constant. So the calculation is showing that we haven't made any mistake as far as the compressor goes. So what will be the compressor work? Compressor work will be, if you recall, m dot Cp T2 minus T1, and we have found m dot. Cp is known, 9.35. Oopsie. Okay, so if we substitute the value 9.35, 1.005, 606, 298, and the compressor works turns out to be 2895 kilowatt. Okay, let's go and verify. So we have already calculated state 1 and 2 device panel. State 1 is the inlet and state 2 is the exit. Of course, this allows very complicated device to be created with 2 inlets and up to 2 exits. Just leave state, a couple of others, I2 and E2 exits as state null. So there is only 1 inlet and 1 exit we are using, which is either of the I1 or I2. Notice that as we selected state 1 and 2, here it became 1, here it became 2. There is no heat transfers, Q dot equals 0. And if we hit enter, the W dot external is calculated as negative 2896. We expect it to be algebraic, and we know external work is negative. So minus 2896 is pretty close to what we found here, compressor work. Okay, let's move on. The next step is what? Finding state 3, which is okay, for state 3, we know It's a constant pressure heat addition. So therefore, P3 equals P2 is 1200 kPa. And what else is given to us? The turbine inlet temperature must be T3 is 1100 degrees Celsius. Add 273 to that. Oops. Okay, the PowerPoint crashed, so I just restarted. So let's go back to state 3. We already know pressure doesn't change during heat addition. And the temperature is given as turbine inlet temperature So we already know pressure and temperature, so state 3 is solved. Therefore, so what is going on between 2 and 3? This is the heat exchanger, you can think, from 2 to 3, and we're adding heat here. And Q dot in is m dot, the higher of the two, H3 minus H2, m dot Cp. M dot is 9 point, what did you calculate m dot to be? I wrote it down somewhere, 9.35. Cp is 1.005. T3 is 1373. And T2, we calculated T2 already, 606. Oops, lost the pen again. And Q dot in turns out to be 7206. Let's go and verify. So we go back to the state panel. State 3, pressure equals P2, temperature is 1100 degrees Celsius, mass flow rate is the same. In the device panel, we go for a device B, which is our heat exchanger. State 2 is the inlet and state 3 is the exit. No external work. 7189. What did we get in? Yeah, that's pretty close. 7189 and 7206. Well within a couple of percent. So the final device or final state also is state 4. So recall that's the turbine exit state. So P4 is P1, and entropy we know at S4 and S3 are constant. So this is our turbine from 3 to 4, isentropic turbine. We know all about state 3 and we need to find T4. Again, if you use our isentropic relationship, we know that we can write T4 or T3 over T4, the isentropic, equal P3 over P4 to the K minus 1 over K, the isentropic formula. Again, we used it for compressor also, equation 11 from the formula sheet. So therefore T4 will be T3 divided by 12 to the k minus 1 over k. T3 is 1373 solving, we get a T4 of 675 Kelvin. That's quite hot. That's the turbine exhaust, which is really thrown out. If we want to find the turbine work, which will be m dot Cp T3 minus T4, 9.35, 1.005, T3 is 1373, 675, and that is 6558 according to my calculations, but I'll not trust it. I'll go and verify. So for that we need to find state 4 first. State 4 P4 equals P1. Remember, that's what completes the cycle. And entropy at 4 equals entropy at 3. Mass flow rate is the same. Device panel, go for device C. State 3 is the inlet, state 4 is the exit. No heat transfer in a turbine. Work is found to be 6553, which is very close to what we got here. And because now we know all the states, we can find the Q dot out. Q dot out can be calculated m dot, which is bigger, 4 is bigger, right, than 1. So you can intuitively write the formula. The amount of heat that is coming out of the heat exchanger, 4 is where it's entering, the air is entering, 1 air is coming out at 1, and heat is rejected. So you can see that m dot h4 is what? How much energy is entering, transported by this mass, and m dot h1 is how much energy is coming out. The difference must be what must be coming out as Q dot out, heat transfer, because there is no other energy transfer in this heat exchanger. So substituting the numbers we already got, mass flow rate, Cp, and T4 was what? 675. Minus T1, which is 298, and that should be about 3543. We already have calculated all the states, so for the device all we need to do is to say 4 is my inlet, 1 is my exit. In a heat exchanger there is no work transfer, so 3532, we have found the heat transfer which matches. And just for the peace of mind, we should always do a TS diagram to make sure if we do the constant pressure lines, we do get a nice cycle, right? 1 to 2, constant pressure, 2 to heat addition from 2 to 3, entropy remains constant in the expansion process, constant pressure, heat rejection. So if we made a mistake, we'll find that these constant pressure lines that I'm drawing will not pass through as expected, because from 2 to 3 pressure should remain the same, from 1 to 4 pressure should remain the same. That's why a constant pressure line should look like they are looking in this TS diagram. So going back, now that we know every device, we have analyzed every device, what are the questions? The first question is find the thermal efficiency. So what is the network? To find the thermal efficiency, the easiest way is to find the network. We have found compressor work, turbine work. If we substitute the two, 6558 minus 2895 approximately here, and that is equal to 3663. We have also found, so this is, I think this is one of the questions to find. I think one of the question is that find the net power output. So this is part of the answer for part B. Let me create another slide. Probably this is the last slide for this problem. So what is thermal efficiency? If you recall, thermal efficiency is W dot net by Q dot in. You could write that as, W dot net and Q dot net are the same in any cycle like this, and Q dot net is Q dot in minus Q dot out and Q dot in. So you can use any of these formulas, but in this case we already know W dot net, which is we just calculated it. How much? 3663. And Q dot in is how much? I believe we did that a couple of slides ago. W dot compressor, Q dot in was 7206. So the efficiency is right about, let's do the division, and it turns out to be 50.8%. Instead of fraction, it's a standard practice to express that in percent. And what is back work ratio? Back work ratio is the amount of work that is consumed back. The turbine produces so much more than the compressor. So it tells you that how much of the work produced by the turbine is eaten up by the compressor. The turbine work we calculated as, okay, this is compressor work 2895. And what is the turbine work? Q in 6558. So that's 0.44 or 44%. So these are our answers for this problem. Let's go verify using test calc. So we have analyzed all the 4 devices. Oops. A, B, C, D. How do you know? The analyzed device will have the inlet and exit state listed. So these 4 devices have been done. Once all the 4 devices are done, that means the cycle is complete. We go to the cycle panel and just say calculate. It gives all the overall stats. Look, the thermal efficiency is 50.8%, back work ratio of 44%, network w.net 3657. So all our answers are verified. So let's go back and get credit for this. So we go back here and click on the problem number, and we can part A, I believe, is the efficiency. And what is the efficiency we got? 50.8%. So let's enter 50.8. How many kilowatt is the net power? 3663. And back work ratio was 44. Let's see if we get them right. Yep, all of them are right. So we have manually solved the problem, verified using test calc, and entered our answer to get some credit for it.